I'd like to thank Dr. Hues for inviting me, not only here today, but also 4 years ago when we first met to participate. And I've really been blown away by his level of impact that he's had in such a short time. But mostly working alongside of him as a scientist and actually as a wannabe engineer. He shows great skill in all of the areas where he has played a role throughout the innovation of his company. So he is a co-author on this study. I'm presenting work that we work together on, but really he deserves as much credit as I do. So he introduced a lot of the background, so I'm going to not spend a lot of time on the clinical aspects of implant stability. That's really not my area of expertise anyway, but just be aware that this has a long history in the scientific literature. So mechanical stability, as you have heard, comes from the initial biomechanical factors that are influenced by these 6 different parameters, of which, for our purposes, we're more interested in the 3 shown here, as well as the long-term healing response. So really, it's a combination of mechanical and biological factors that are required for successful implant osseointegration. And Dr. Hues really emphasized that I don't need to lecture you about bone mechanical properties as I would for my engineering students. So I'll try to keep this fairly short. What we're really interested in is the trabecular bone properties. And these are orders of magnitude lower than the cortical bone. So while most research studies have focused on cortical bone for understanding modulus, ultimate strength, and strain, really the trabecular bone has a lot more variability. And it's related to its density, which also has a lot of variability. So there's a direct relationship between modulus and density. There's also a direct relationship between the ultimate stress and the density in trabecular bone. And as you can see from the curve, trabecular bone has a very long plastic region after yielding. So the initial elastic region is the kind of straight line at the beginning, and then the horizontal line represents a large amount of plastic deformation that can occur. And the area under this curve is the energy that's absorbed during this deformation. And that's correlated to the material toughness. So while cortical bone is fairly brittle, it doesn't have a lot of plastic deformation after yielding, trabecular bone does. Trabecular bone is also related to the rate of loading. So if you impact it, it will have a much higher stiffness and strength than if you load it gradually. And it becomes more brittle with high rates of loading. If you apply time as another variable during loading, then bone has this viscoelastic property, the ability to creep over time and absorb energy. But a lot of people don't talk about viscoplasticity. So anytime you load above the yield region, then you're going to generate plastic deformation, and that's also a time-dependent response. So when Dr. Hues talks about the time-dependent low plasticity of bone, he's really talking about a viscoplastic response, which occurs immediately after a viscoelastic response. And this plasticity is most importantly related to the collagen component in the bone tissue. So we think of bone as being a solid mineral, but actually the collagen fibers are mineralized And that collagen has its ability to viscoelastically deform like any other polymer. So you could really think of it as a polymer that has this mineral content as well. And more recently, people have been trying to understand how the mechanical environment in the bone tissue will affect the remodeling or the response to changing loads or growth or development. And this field of science is called mechanobiology. So people have recognized for a long time that bone optimizes its geometry to the direction of loading. This is called Wolff's Law, and that adaptation is proportional to the magnitude of loading as well as the frequency of loading. So if you apply very low magnitude or frequency of loading, then bone will resorb. If you increase the frequency of loading, you can get increased density of bone and increased properties. But if you exceed a certain threshold, then you're going to damage the bone. So what we want to avoid is excessive strains that would lead to pathological bone resorption. And the idea of osseodensification that Dr. Hoyce had when we first met was that he wanted to maintain not only the density but also the structure of the bone so that, or even improve the stiffness and strength of the bone by reorganizing it in order to improve the biomechanics as well as the mechanobiological response of the bone. So he asked me to work with him to validate this technique, this idea, and do it in a well-controlled laboratory experiment. So we used the materials testing machine to not only apply the surgical procedure, the displacements, but also to measure the forces and torques that were generated during the procedure. So we attached our handpiece into the materials testing machine and then programmed the displacement to follow a clinical protocol. And we needed a model of our tissue that allowed us to do repeated testing on different groups with sort of limited variables in terms of the bone density across the surface and, you know, not the complex geometry that you would have in the mandible or maxilla. So we selected pig tibias, the proximal tibia, and we removed the cartilage and subchondral bone to expose the trabecular bone. So it was a fairly uniform and homogeneous type of tissue. And then one of the first goals was to kind of verify the clinical safety and the ability to control this procedure as a function of time, control the heat generation as an effective way to create the osteotomy for placing an implant. And so we measured heat generation, we measured the drilling process, we measured the implant process. And then our scientific hypothesis was that osseodensification increases the primary stability and also the density and the bone implant contact. And so we used insertion torque, removal torque, Ostel ISQ, micro-CT, and histology, as well as a couple other imaging methods to try to address this hypothesis. And we ended up placing 72 implants in 12 tibial plateaus using 3 different preparation techniques. So our control group was a standard drilling procedure, and we had 2 experimental groups. Really, this one is more of a control. So we used the Densa-burr both in the clockwise cutting direction to extract bone similar to drilling. And we also, the novel feature was reversing the direction for counterclockwise to densify and compact the bone down into the tissue. So that was the Osseodensification group. And again, we wanted to look at the initial clinical process to verify that, as well as to look at primary stability with 2 straight implants. So we placed the more traditional Brandemark macro geometry implants with a 4.1 millimeter and a 6.0 millimeter diameter. And then we measured we imaged the bone morphology in a few different ways, as I mentioned previously. So what we tried to do on our materials testing machine is recreate the clinical procedure and control it. So we followed the same sequential expansion process that you do in your own practice, following the instructions for use guide from Versah. So we started with a pilot hole, and then for the drilling, we continued with 1 millimeter increments up to 3.8 millimeters, and then we placed the 4.1 millimeter implant. And then we took that implant out. We did 2 more sequence of expansion steps or drilling steps at 4.8 and 5.8, and then we placed the 6.0 millimeter implant. And each of these sequential steps was controlled or programmed to follow this bouncing motion that hopefully you're familiar with. So we did a 4 millimeter downward stroke, and then a 2 millimeter upward stroke, another 4 millimeter down, 2 millimeter up. So we went through a series of 6 kind of bouncing steps to a final depth of 14 millimeters. And then we placed 11 millimeter deep implants. So the implant didn't bottom out. There was a gap at the apex of the hole. And during each of these diameter drilling steps or densification steps, we measured how much compressive force we had to apply to penetrate the burr into the bone, as well as any torque, reaction torque that the bone was experiencing. And we did this for a few different motor speeds to verify the clinical speed, which is the best for operating this. And we placed a thermocouple 0.5 millimeters away from the final diameter of the osteotomy to measure the maximum temperature increase that occurred during this procedure. So osseodensification does require that you press with more force than you would when you're drilling, because you're encountering the bone and actually compressing it. So the bone is going to apply a reaction force against you, pushing you back out. As opposed to drilling, if you're extracting bone, then that extraction of bone could actually create a reaction force that pulls you in slightly. So it is different than drilling procedure. We did measure higher torques and forces during the drilling process, and it was correlated to the diameter of the burr. So as you get to the larger and larger burrs, you're going to experience that you have to press harder and harder to get it to condense the bone. But this is actually a way of controlling the process. So depending on the density of the bone, you're going to have to apply a certain amount of force that's proportional to that. And it gives you a sense of the quality of the bone that you're encountering. And lower speeds require more force as you apply it. So the optimal speed was 1100 RPMs, so we recommend that you follow the osseodensification procedure using a high RPM speed on your motor. This also reduces the amount of time that it takes to complete the procedure, which is also important for the amount of heat that's generated. So the bouncing motion is critical, but also the high speed reduces the amount of time that you would be generating heat. So osseodensification does increase the temperature around the osteotomy. as does normal drilling. So we saw about 3 degrees Celsius increase with our standard drilling groups and our extraction drilling groups. And osseodensification was about 6 degrees Celsius. So slightly more, but with the irrigation and with this controlled slow bouncing procedure, this is still well within the physiological range for preventing bone necrosis. So we're not exceeding the temperature threshold, and we're also applying this over a relatively short amount of time, which are both factors for bone necrosis. So looking at the stability of the implants that we placed, we saw insertion and removal torques similar between the 2 types of drilling procedures, but they were increased by a factor of 2 with osseodensification. So the insertion torque, obviously you're threading the implant into the osteotomy, and you would expect to have a certain amount of insertion torque. We were really surprised and happy with the reverse torque, and we think that had some implications for demonstrating the stability of the bone. So you're not just creating threads when you're reversing back out, but there's actual compression of the implant by the bone that's creating that reverse torque. And so that may be important. We did measure ISQ. We didn't see a significant difference between osteodensification and drilling. ISQ measures a different type of biomechanical stability than insertion torque or pull-out testing or lateral displacement testing. So there are different ways to measure mechanical stability. And there hasn't been a lot of correlation shown in the literature between these different types of measurements. So ISQ is great for clinical documenting of osseointegration, where you can't do a reverse torque test. But in our case, because we weren't seating the implant all the way to the bottom of the hole, we think that had an impact on the ISQ readings for a lot of our tests. So they were all above the goal that we would hope to achieve, but there wasn't a difference between the 2 groups. So that's one of the conclusions. And as Dr. Hues showed in his slides, we were really impressed by the ring that seemed to appear during this process, and maybe if you've tried drilling one of these tibias, you've actually seen it for yourself and experienced it. So it's quite obvious that something different is going on here. We're not extracting bone particles. The bone particles are clearly going into the osteotomy. So that's fairly obvious when you compare it with the drilling technique where you see bone particles coming out. And we also noticed that the interior surface along the edge of the hole was smoother, and that showed itself on scanning electron microscopy as well. We had a smoother hole that's due to the autograft particles into the trabecular pores. On bone mineral density, there's clearly an increase, this halo of brighter CT image around the osseodensification holes. And that also occurs at the apex of the hole. So we were interested in how thick that compacted layer of bone is. And it varies from the top of the hole to the bottom of the hole. So it ranges between 0.1 and 0.3 millimeters around the wall thickness. And it's between 0.5 and 1 millimeters at the apex of the hole. For bone implant contact, we were able to get histological sections of a few of our implanted implants. So Again, this clearly shows those autographed bone particles in the region along the edges and near the bottom of the implant. And we also were able to measure the bone-implant contact and see more than a 3 times increase compared to standard drilling. And Dr. Sleet has also done his own histological study, and other animal studies have looked at the bone implant contact response. This is just time 0, but now we're able to see similar results at time 0 as well as early healing responses in animal models. So one of the important features Dr. Weiss wanted me to make you aware of is the springback effect of the elastic deformation or the viscoelastic deformation. As you're applying the Densibur into the tissue and compressing it or expanding the osteotomy, you're plastically deforming it, but before that happens, you're also elastically deforming it. So when you take the burr out, the bone is going to recoil if it's still structurally intact. And what we noticed was that did occur. So for a 5.8 millimeter burr, the osseodensification procedure resulted in a 5.4 millimeter final diameter. And this was measured with a micro CT. So we saw about a 90, our final diameter was about 90% of the burr diameter. This is different than with a standard drill. We actually saw that the standard drill hole was slightly larger than the maximum diameter on that drill. So there was a certain amount of vibration or chatter that occurred, and it created a slightly larger hole. So while you're used to maybe undersizing, with osseodensification, if you're going to undersize, you really can't undersize nearly as much. You want to keep it within a fairly close tolerance to the burr diameter with your implant diameter. And it depends on the density of bone. So if you're in very low density bone, then you have a little bit more forgiveness. But in higher density bone, you're probably going to have more springback. And so with the final few minutes that I have, I wanted to go through a few comparisons with the literature. Other people have shown bone compaction with osteotomes, so you can see a similar halo effect created around these X-ray microsections from other laboratory studies. And with this, they also see increased stiffness and strength, demonstrating higher primary stability as you compact that bone. In addition, you could look at the healing response of compacted bones. So the first 2 images here show 2 weeks after implantation. The compacted bone is obviously more dense around the implant than the drilled bone, and that higher density or higher bone implant contact eventually will catch up between the two for longer healing times, but there is this early healing time response where you have continued higher implant contact and density. And this study wasn't with an osteotome, this was with a lateral expander. So there are differences that can occur between those processes. So not all types of compaction are the same. This is a more gentle type of compaction. Compared to, again, this was a osteotome study looking at healing. And again, they saw that the osteotome technique increased the bone implant contact, the bone area ratio initially compared to the control, which was a drilled sample. But by 8 weeks, the difference the significance of the difference had gone away. And also, what many studies have pointed out during osteotome compaction is fracturing that's occurring in the trabecular structure. And that could also be important for the healing response when those fractures occur. There is an alternative way of compacting bone by autografting and using those autografting particles to compact into the bone. So this has been done for orthopedics around femoral total replacement stems. And this increases the healing when you autograft particles. So the osseodensification is actually combining the lateral expansion and the autografting into one procedure. And we think that that's an important distinction. So Dr. Trissy is going to talk extensively about his research and his current work with osseodensification. But I just also want to point out how the increased density and primary stability that we see in our study is related to the amount of micromotion that we would expect to occur, and how that we expect will impact the healing response. So improvements, basically the discussion is that we expect to see improvements in the healing response, even though our study, we just looked at the day 0 response. In addition to reducing micromotion, we're also creating residual strains. So we're laterally expanding the osteotomy and creating this plastic deformation. When we're placing the implant, we're also further elastically deforming and compacting the bone slightly. And those residual strains can also be beneficial for healing, as long as they're kept within the threshold below microfracture and the pathological response. So the take-home messages, really what relates to your clinical experiences, is this is a type of compaction autografting. So it's densifying in 2 different ways. And this enhanced bone density allows you to have higher material bulk in the form of bone matrix, cells, biochemicals, as well as bone mineral density at the osteotomy site. So the enhanced region is right along the implant where it's necessary to help improve the osseointegration. The residual strain is demonstrated by the smaller hole that was created through the springback effect, and residual strain is also beneficial for osteogenic activity, as well as the primary stability for keeping micromotion at this interface below the pathological threshold. So this is the basis for Dr. Huey's brochure, which I'm sure you've probably seen. So he has really been interested in the scientific validation for this procedure. So please refer to our published work in the International Journal of Oral Maxillofacial Implantology. It's available online and should be in press shortly. So these were the conclusions from the biomechanical validation study that I did. So with that, thank you very much for your attention, and Thank you for having me.